this workshop. Okay, and I am talking about, as you see from the title, coupling black boxes, black box solvers. This is a joint work with that we are doing with Eric in this period here, plus some older works that I carried out with Silvia Falletta and Gianmarco Manzini. So first of all, let me tell you what, for me, the name of the game is. So what is, do you see, because I see this, you see the complete slides? Because I have the Zoom.
Yes.
Okay, so perfect.
I see everything. So if anybody doesn't see, please complain. Okay.
So the framework is the one where that we are used to, everybody of us, I think. So I have a large continuous problem that I somehow rewrite as in an equivalent formulation as a set of local small problems coupled, and I write down an iterative scheme to solve this coupled system of problems. And in many applications, the bulk of the computation is the solution of the local problems. And we have available efficient solvers for treating these local problems. So the idea, and they are efficient because either I really wrote some very efficient algorithm, or even because they have been optimized at compiling time. So in a very hard, in a very end user sort of way. And I want to treat these solvers as black boxes. And many times these solvers, I have an incomplete control of what goes on under the hood. So I really want to treat them as black boxes. And what do I mean by black boxes? There are different levels of meaning that I will focus on in this talk. The level 0 is simply the algorithm is closed. I need to use the local solver algorithm as it is. I cannot go inside the code and program or tweak it in a way that makes it better for my coupling method. Then there is the infinity level. That is, I simply have something where I put on some input and it gives me my output, and I do not have the slightest idea of what algorithm is used and what goes inside in the method. And then there are several intermediate level where I have a partial information or control of the algorithm. And for example, if I know that I'm using finite elements, I can fix the mesh size, but the input and output have been fixed by the person who programmed my solver, and I have to use them as they are. Okay. Let me underline that it's very rare, unless you programmed the solver yourself, it's very rare that you really know everything that goes on in a local problem solver, because there are always approximations that are made at the moment of programming that were not thought before. For instance, the choice of quadrature or different things. So the idea that you don't have the complete control of the algorithm inside the local solver is something that's really real. Okay. And when you want to use the local problem solvers as black boxes, there are different types of problems that you need to face. So first of all, there are problems really related to the implementation of like an outer cycle that calls for the local solvers. This is kind of an informatics problem, And I put a double question mark because I realized that every time I try to figure out which these problems will be as a mathematician, I greatly underestimate them. So I will still try to figure out them, but I am aware that I am underestimating this thing, and I am concentrating on the mathematical problems that you encounter. So you have these local solvers for your small problems, and you want to design a global solution strategy using the available local solvers. You want to propose strategies that ensure the stability of the coupled problem, to give condition ensuring accuracy of the solution of the coupled problem, and we'll see what I mean. Of course, you would like it to ensure scalability. So if you can split the same problem in smaller problems, the execution time, you would like to diminish it proportionally, and ensure fast convergence with mean design suitable preconditioner. And of course, the black box idea is that all of this, you are not allowed to modify the local solvers. Okay, so going on with an abstract framework, you have your original continuous problem. This is quite natural, but you have a problem of the form AU equals F in an Hilbert space, where A is a nice linear operator. And you somehow manage to represent, have an equivalent representation of your space V as the product of Hilbert spaces, subject to a coupling condition. In particular, you introduce a multiplier space and linear operator that goes from the small Hilbert spaces. I mean, small, they are still infinite dimensional, but they are smaller than your original space when you discretize, to the dual of the multiplier spaces, and you identify your original Hilbert space as the kernel of your of the sum of the linear operators. Okay, and then you are able to split. You assume you are able to split the operator A as the sum of the contribution of linear operators AL on the spaces BL, and the same for the right-hand side. And in this way, you can write down an equivalent formulation in constraint form. That is, you find U in the kernel of B, such that for all V in the kernel of B, AU tested on V is equals to F tested on V. That is, AU is equals F as seen as an element of the dual of the kernel of B. Or you can write an equivalent formulation in saddle point form. So you look for U in V and phi in the multiplier space, such that AU minus B transpose phi is F in V prime, and BU is 0 in phi prime. And up to now, nothing new. The idea is that you make some assumption on the local problems, local operators, of course. You assume that the kernel is finite dimensional and that it's equal to the kernel of its adjoint, and the linear operator, the local linear operator, are coercive on the orthogonal complement to the kernel in V in the local Hilbert spaces. Okay, to simplify, let's assume something stronger, that is that all AL are invertible. Then you can like do a sure complement kind of argument and write down an equation for the multiplier that I will call Steklov-Poincaré operator, because in the domain decomposition, if the multiplier is the trace of your function on a skeleton, then you have a Steklov-Poincaré operator. So you will have a problem of this form as phi equals minus BA to the minus 1 F, where S is BA to the minus 1 B transpose. These are already at the continuous level, okay? And the idea is you want to write an iterative solver for this problem. And writing an iterative solver for this problem, of course, implies solving problems of the form AX equals G that can be done in parallel. And that is the basis of, for instance, domain decomposition or in many different forms. In general, we would like not to assume that A is invertible. So we would like to consider A not invertible, but we assume that the kernel of A and the kernel, which is equals by assumption to the kernel of its adjoint, is finite dimensional, and that A is coercive on its orthogonal complement. And then if this assumption holds, I can define a pseudo-inverse for my linear operator A, taking value in the orthogonal complement, and I can see that I can use the approach that is used in the construction of FETI preconditioners. So I can see that U verifies U equals the pseudo inverse applied to F plus B transpose times the multiplier, and plus something that we know lives in the kernel of A. And if I plug this expression in the equation in the constraint, I obtain an equation of this form, okay, where this is, before I had BA minus 1 B transpose phi equals BA minus 1 F, now I have BA plus, which is the pseudo inverse B transpose phi, plus BZ, where Z is an element of the kernel which is unknown, equals minus BA plus F. And this is an equation in the dual of phi. If I need then an equation to get control of this element of the kernel, and in order to get such an equation, I test the first equation, which is well, I had AU minus B transpose phi equals to F. I rewrite it like that. I test it with an element of the kernel, and I use that the kernel of the operator is equals to the kernel of its adjoint. So if I test AU times an element of the kernel, this is U times A star, the element of the kernel, which is in the kernel of A star, and vanish, then this part here vanishes, and I obtain this condition on the multiplier. B transpose phi equals minus F as an element of Z prime. So of the dual of the kernel of A. And so I have a new formulation that I still call Steklov-Poincaré problem. So I have an element in V prime, and I look for a multiplier in phi, and then an element of the kernel of A, such that this saddle point problem is satisfied. This turns out this is a well-posed problem if our original problem was a well-posed problem. And well, here I have a smaller problem here because it's in the space of multipliers, which we will see in many instances of our abstract framework is a smaller space. And the one that acts as a multiplier in this saddle point formulation is in a finite dimensional space. And of course, applying S implies pseudo-solving local problems in which I split my original global problem. Okay. So at this point, we ask, when do we discretize? Okay, of course. Eventually, we will have discretized everything, of course. But where we think of introducing the discretization, it gives you different points of view on how to look at the algorithms. It doesn't necessarily gives you different algorithms, but different points of view and different way of writing sufficient conditions, for instance, for convergence. There are, you can discretize the problem at different levels. You could discretize it at the level of the starting global problem. This gives you the usual algebraic point of view of having the global problem becomes a huge linear system of equations, and then you parallelize it by splitting it as coupled problems and so on and so forth. Then you can discretize it at the level of the coupled local problems. This is, for instance, what gives rise to non-conforming domain decomposition, for instance. Or you can think of writing down the Steklov-Poincaré problem at the continuous level and then discretize it as it is. And then you could also discretize directly the iterative scheme, which would mean that you have a convergent iterative scheme and have, for instance, a preconditioner, kind of a continuous preconditioner. But I will stick to these two kinds of discretization. Okay. So let's think about discretizing the Steklov-Poincaré problem. So I have my Steklov-Poincaré problem, which, as we saw, is a saddle point problem where the primal unknown is the multiplier of my original coupled system, and the multiplier is the kernel of the operator A. Remark that the kernel of the operator A is finite dimensional, so I do not need to discretize it. I look for a Galerkin type discretization, so I introduce a finite dimensional subspace of my multiplier space pi. And then, of course, I don't have a continuous solver for my problem, so I have to replace the pseudo-inverse with approximate pseudo-inverses that are reduced to replace the Schur complement or Steklov-Poincaré operator or whatever I want to call it by an approximate version. Remark that I could also think of approximating B and B transport, but for simplicity, I stick to approximating only the solution step. Okay, and this A plus delta will be my black box solvers. If I do this, I end up with a discrete problem that is in saddle point form, where I have a Galerkin type formulation with a non-conforming approximation of the bilinear form, which is this object here. And I ask myself under which minimal conditions, possibly minimal conditions, can I ensure that the discrete problem is well posed and the discrete solution is actual an approximation to the continuous solution of my original problem. And well, first of all, I'm talking about approximation, so it's quite natural. Usually approximation happens when you know that your solution has some more regularity than the simple regularity of belonging to your Hilbert space. So I consider I need to consider some way of measuring smoothness in my abstract framework. And I do it by introducing like a smoothness scale. So I introduce spaces Vs for S, and here I should have written greater or equal than 0 because I set B0 equals to V. And then Vs is the space where I gain S degree of smoothness with respect to V0. And the same I do for the space phi, where phi 0 is phi, and phi s is smoother function of s degrees of smoothness. And I need, of course, my operation to preserve the smoothness when they go from, for instance, from Vs to phi s. If the function is in Vs, the object, and I apply an operator that brings it in phi, the result must be in phi s, and something like that. Then kind of a natural assumption for my black box solver is that if I know that the solution has some extra degree of smoothness, my approximate solution is a good approximation of my actual solution, okay? And so this writes the norm in V of A plus delta minus A plus of F in V is less or equal than a constant time a mesh size delta to the power S times the norm of the A plus F, which is let's call it continuous solution in VS, okay, the higher smoothness norm. Actually, this is even too much for the well-posedness of my discrete Stekel-Poincare operator, and it is sufficient to ask that once I apply B to A plus delta minus A plus F, and I measure the norm of this object in the dual of phi, then if A plus F is smooth, then this guy is small, and it's smaller than delta to the power S times A plus F of S. In particular, this implies that I could use solvers that are precise only close to the region where my operator B acts, which might give a nice, how do you say, gain in designing efficient schemes. Okay. And then I need my, here should be a phi h. Sorry, I first or second misprint. The space phi h needs to verify some approximation property of this form. So if phi is regular, then I can approximate it to the right order with element of the discrete space, and also some kind of inverse estimate. So my discrete functions have a certain degree of regularity, and the stronger norm is less than the mesh size to the minus s times the weaker norm. And also here I have another misprint. This should be phi, because we are in an abstract framework. And then if I am in the framework where A is not invertible, but it has a non-zero kernel, I need to be able to control the kernel part of my Stekel-Poincare saddle point problem with the elements of the discrete space phi h. So I assume that there is a fixed space phi 0, which controls the multipliers Z. These are the elements of the kernel of A, and this is contained in all my discrete spaces. Okay, and it satisfies an IMSUB condition of this form. If I have all these assumptions, then it is possible to prove that there exists a constant depending on the constants in the assumptions, such that if the delta, which is the kind of the degree of approximation, let's call it the mesh size, even if we are in an abstract framework, so we do not necessarily have a mesh underlying this approximation, but if the mesh size for the approximate solver is less or equal than k times the mesh size for the multiplier, then my discrete Stekel-Poincare problem is well posed, And we have this kind of error estimate where once again, another misprint here, it should be phi. Okay. Observe that the condition delta less or equal than kh is basically equivalent to ensuring that an if subcondition is satisfied, allowing to control the space phi h with the space v delta that I don't know about, but it's underlying my black box solver, A plus delta. Okay, and such condition may be quite restrictive of difficult to enforce. So I will have to think of ways of stabilizing this problem. Okay. But now let's come to some concrete examples. So the first example, and here we go to domain decomposition. I will always consider this simplest of model problems, so the Poisson equation with a zero boundary condition on the exterior boundary, and I will somehow impose the exterior boundary condition, so I will totally forget it and never write it in the following of the talk. And the three fields formulation was introduced by Brezzi and Marini in the 90s, and it's a quite clean way of rewriting your continuous problem as a linear system of smaller problems at the continuous level, and it relies on the so I have a non-overlapping decomposition of my domain omega into domains omega L. Gamma L are the boundaries of the domains omega L, and sigma is the skeleton. And I look independently for three unknown fields. So the function u in the bulk of the subdomains, the function its trace, which will be my multiplier phi on the skeleton on sigma, and then I will look for the outer normal derivative, which lives in subspaces h lambda L, which are h minus 1/2 of gamma L. And the three fields formulation looks like this. So I look for UL, lambda L for each L, and phi that lives in the trace on the skeleton of each one of the whole domain, such that for all test functions in the same space, I have these three equations. These two equations, the first two equations, are basically minus Laplacian of u equals to f in the subdomain omega L with a boundary condition UL equals phi imposed by Lagrange multiplier in the spirit of the babushka method. And once, if you solve this, you know that the lambda L is the outer normal derivative. So the last equation is simply continuity of the normal derivatives, okay? And so if I discretize all the spaces with the Galerkin method, I end up with this large discrete system, and then I can, well, first of all, if I study the whole system, I can bypass my my abstract analysis and do an analysis of the problem. But here I have a double saddle point problem, so I will need to impose two if subconditions, which are the lambdas, the lambdas that represent the normal derivatives must control the trace variable, and the u must control the lambdas. If this is satisfied, then I have this error, this optimal error estimate, where the norm 1 star is the broken H1 norm. So of course, here this kind of discretization relies on the fact that I look for pH in, and let's go here, in this space phi, which is the trace, the restriction of H10 of omega L to the skeleton of the decomposition. Okay, so in a way, it's a conforming discretization of the skeleton variable, and asking for this conformity, so asking that phi H is in phi, basically requires me to impose for phi continuity on the wire basket. In 2D, this is no problem. I have continuity in the cross point is easily imposed. In 3D, this is quite restrictive. It turns out that one can relax the conformity requirement on phi and define phi allowing this phi H allowing discontinuity on the wire basket. And I still get a quasi-optimal error estimate where I lose a factor of a logarithm of big H over small h. Okay. To solve this problem, with a Steklov Poincaré form, would reduce to, okay, I have a guess function phi, I solve my problem with my discrete problem with a babushka Lagrange multiplier Dirichlet solver, which I will consider as a black box. So I use it as it is. Then I take the output lambda and I plug it in the last equation. And this will be my Steklov Poincaré iterator, let's say. In order to do that, I, of course, have to have a babushka Dirichlet solver that has in output the Lagrange multiplier. And more in general, if I want to use the trace of U as a guess, the residual that I will have to compute is the jump of the normal derivatives, which requires that my black box gives in output a stable approximation of the outer normal derivative. And this is not always available. In general, if we ask ourselves, what does what do Poisson solver let you prescribe, and what kind of output you can be sure of retrieving? Of course, you are free to prescribe the differential operator, the right-hand side. You are free to prescribe generally non-homogeneous Dirichlet boundary condition and the non-homogeneous Neumann boundary condition. It's quite reasonable to assume that in output you can get the values of the solution at the boundary. The outer normal derivative is more rare, so it makes sense to rewrite, to write down our Steklov Poincaré iterator to be as general as possible in the choice of the black box solvers in such a way that it uses Neumann solvers and imposes the continuity of the solution, which implies that we are really in the framework where the local solvers are not necessarily well defined, but might have a non-zero kernel. Okay, so we might have floating subdomains, and the solution is only determined modulo constant. And then we can use the FETI approach that I talked before in the abstract framework, and this gives me a saddle point problem with a scalar multiplier for one scalar multiplier for each subdomain. If I discretize it, this time phi is an outer is an approximation for the outer normal derivative, so it only needs to be L2, and I can prove that the discrete problem is well posed provided the phi zero space, which I talked before, which is defined in this case as the phi in L2, such that the phi is a constant on each common edge between two subdomains. Okay. And then I can use any suitable method to solve my Steklov-Poincaré problem. And I replace the solution of the Neumann problem with a black box. And if the black box is sufficiently fine, I have a well-posed problem. So let me see, I have 10 minutes. So what can go bad? So this is the three fields formulation. And I choose this mesh here. And I solve the three fields formulation as it is. As you can see, I get some very nasty instabilities for the phi, for the trace solution. Okay. Then once you project this solution and get you still get a nice error. But the problem is that if the iterations are on this functions, so this is the unknown, this is the functions that you are trying to retrieve with your iterative scheme, then your conjugate gradient or whatever iterative method you use will not converge or converge very hardly. And then the idea is that you can add some kind of stabilization. And here we have on these different meshes, the comparison between unstabilized and stabilized method. And the stabilized method is the one that gives you these other two solutions. And you can see for the non-stabilized method, if the mesh on this n is the number of nodes per edge of the discretization of the multiplier. So as small n increases, the condition for the well-posedness of the method that I had in the abstract formulation is violated more and more. And at a certain point, the iterative procedure doesn't converge anymore. And then you can add stabilization and it converges. Let me skip this because I have very little time. What can I do for stabilization? Let's go back to the three fields. Okay, so I have this A, B transpose B is my black box Babushka-Dirichlet problem solver. And this is my Steklov-Poincaré operator. And I can stabilize by adding this term. Okay, so I add a residual term because for the continuous solution, U is equals to phi, measured either in a wavelet realization. This is something proposed like 20 years ago, of an H of 1/2 of gamma scalar product, or in a mesh dependent SUPG-like bilinear form. The point is that the new Steklov-Poincaré operator is apparently, the new Steklov-Poincaré operator has this form. And you can see that I have something inside the black box solver. So this is not good. Turns out that if I have this assumption, so if for my Dirichlet Lagrange multiplier method, the dimension of lambda h is equals to the dimension of the trace space VHL on gamma, then I can use the last equation to obtain the boundary value. And then I can use a And then I can solve the first equation without, that's not touched by my stabilization, and then retrieve the multiplier. Turn out I managed to implement this as a post-processing. So the implementation is such that if I had my original Babushka-Dirichlet solver, I can use it as it is and account for the effect of the stabilization in a post-processing step. So let me jump to this and see if this is worth it. So this is the three fields formulation, unstabilized and stabilized. Table 2 and table 4 are the errors. So if you measure the error for the U, the error for the U is much better in the unstabilized method than in the stabilized one. However, the cost per iteration, I mean, in the plain formulation, well, the cost per iteration is lower, of course, but the number of iteration is too much. So the method does not converge in the number of iteration that we fixed as a maximum. And it turns out that the more expensive stabilization gives you actually the better total cost. To end, since my time is finishing, let's go back to the abstract framework and try to write down a stabilization. So the point of the stabilization here is that we want the stabilization not to affect in any way the black box solver. So the idea is to build a new stabilization that has as ingredient that only acts on the Lagrange multiplier without touching the black box solver. The ingredients are a subspace of my discrete multiplier space, which is coarser in such a way that V delta, the assumption is delta less than KH is satisfied for H equals H star. Okay, so for the subspace phi H star, the problem would be well posed. And then I control the difference phi H minus phi H star by introducing a bounded projection from the finer to the coarser space and a computable bilinear form satisfying a norm equivalence. So an equivalent scalar product for my phi space on the kernel of this phi H star. And then I add to my Steklov-Poincaré operator this term here, which basically penalizes phi H minus its projection onto the coarser space in this scalar product that I introduced, okay? And then I can prove, and this is a joint work with Eric Burman, as was the abstract formulation and the minimal condition for the abstract formulation, that if H star is smaller than K delta, then the bilinear form corresponding to the stabilized problem, if the kernel is zero, the bilinear form is invertible. In general, the Steklov-Poincaré problem stabilized is well posed. And we have this kind of error estimate, where now I have this H star as that enters the error. Okay, I finish by commenting a little bit on how I can build the ingredients to construct the stabilization in the domain decomposition framework. So here the spaces are either H1/2 or H-1/2, depending on whether my multiplier is the trace of the function or the outer normal derivative. So I need to bind to build H1 or H1-1, H1/2 or H-1/2 bounded projector. The H1/2 bounded projector can be built by building projectors that are simultaneously built in L2 and H1. There are several recipes in the literature. One can use uniform L2 projector that for graded meshes can be, if the grading is sufficiently, sufficiently shaped regular meshes, then there are several results that ensure that the L2 projector is bounded also in H1. One could use projector based on dual meshes or projector based on dual bases. And by duality, you can construct H-1/2 bounded projection. So the L2 projector onto continuous piecewise linear turns out to be bounded in H-1/2, provided the same grading assumptions are satisfied as for the H1/2 projector. Then you could use a projector based on dual meshes if you use for your multiplier space the one living on the dual mesh, or you can use as phi h the space spanned by the dual basis, and you have projector on the dual basis. Let me skip this. No, okay, maybe I have time to finish this. In order to construct the bilinear form, we can rely on some localization results for the H1/2 norm and the H-1/2 norm. So I assume that I have a mesh of my gammas, of my interface, and that I have nodes y, and for each node y, I consider a patch of elements, the patch of elements that share y as a node. And then I introduce a set of function E tilde y in L2 of gamma L that satisfy this assumption. The support of E tilde y is the patch of elements that has y as a center node. The integral of E tilde y is 1, and the norm in L2 of E tilde y behaves like h star to the -1/2. Then I can prove that if a function phi is orthogonal to all these E tilde y's, then the norm of phi in H1/2 gamma L is equivalent to the sum over all nodes, the norm of phi in H1/2 of the patch centered on the nodes. This guy here in our abstract, in our domain decomposition framework is treatable because it's localized. So we can think of, we are able to compute something that's equivalent to this. And if we define the projector orthogonally to such a set, this will give us the equivalent norm that we need in order to construct the stabilization. For the H-1/2 norm, there is a similar result with different conditions on the E tilde y, but in particular, these conditions, both these conditions and these conditions are satisfied by piecewise linears. So if you project orthogonally to piecewise linears, we have these localization results. Conclusions, I skip preconditioning. We have different strategies available to couple black box local solvers. And we showed some minimal assumptions that assure that the underlying subconditions are satisfied, and then the coupled problem is well posed. We can employ stabilization technique if these assumptions are not completely satisfied. And of course, we need to design good preconditioner that do not touch the black box solvers. We would like to be able to monitor the validity of the assumptions so that as we go by, we know that our black box solver has sufficient approximation to ensure that the Steklov-Poincaré problem is well posed. We would like to account for using, for instance, adaptive solver that will introduce some nonlinearity in the overall problem. And that is basically all I had to tell you. So thank you very much.